Welcome to the second part of Introduction to Number System. Okay, so in this approach, repeated multiplication by 2 method. To convert decimal fractions to binary, repeated multiplication by 2 is used until the fractional product is 0 or until the desired number of decimal places. The carry digit or carries produce the answer with first carry as the MSB and the last as the LSB. So you have given this number, the fraction 0.3125 decimal. You need to convert it in binary, so it becomes something like that. But how you can get it, let's check it here. So 0.3125 multiply by 2, as it says, to convert it in binary. Base of binary is 2. If it says to convert it octal, multiply by 8. If hexa, multiply by 16, something like that. So if you multiply 0.3125 by 2, it becomes 0.625. So remember this 0, so it is written as red color. It will be needed. So, or you can write within the carry as 0. 0. Again take the 0.625 multiplied by 2, it becomes 1.25. Take the 1 as carry. Now 0.25, take 0.25 multiplied by 2, 0.50. And again carry 0 here, so again 0.50 multiplied to 1.00. When you get 0 after the decimal point like 1.0, then you stop the multiplying. Okay, otherwise you can keep going up to certain point. Now look at the carry. So the bottom carry is known as LSB, the top carry is known as MSB. It is pretty much reverse what we saw in the last slide. So if you rearrange this from MSB to LSB, it becomes 0101. So 0101. So this point is for this point. So this is the conversion from decimal to binary. Conversion between decimal and other bases. Decimal to base R. Whole numbers. For whole numbers, we need to do repeated division by R. For fractions, we need to do repeated multiplication by R, which is pretty much similar what we discussed before. Conversion between bases. In general, converting between bases can be done via decimal. Say you suggested to do the conversion from base to octal maybe. So then you need to convert base to decimal, then decimal to octal, or other way around. Octal and hexadecimal number. The conversion of binary, octal and hexadecimal plays an important part in digital computer. Each octal digit corresponds to 3 digits, and each hex digit corresponds to 4 binary digits. The conversion from binary to octal is easily accomplished by partitioning the binary number into a group of 3 each, starting from the binary point and proceeding to the left and to the right. Conversion from binary to hexa is similar. Conversion from the octal or hexadecimal to binary is done by procedure reverse to the above. So let's look at some example, then it will be clear what we try to say here. So binary to octal conversion. So you have given this binary number, you need to convert it to equivalent octal. So for octal base is 3, that's why you need to make a pair of 3 bit of binary values like 001, then red portion, 011, green portion, 111, black portion, then 10. So you can put in front of 10, 010. So now write the equivalent binary number. Now equivalent actually octal number. So 10 is 2, 111 is 7, 011 is 3, and 001 is 1. And for this fraction, so also take the 3 bit, but you start 3 bit from here, 101, not from here. Okay, so 101 becomes 5 and 110 becomes 6. So this is your equivalent octal for these binary values. So for converting octal to binary, you need to do the reverse calculation what you have done. Just look at the next one. You have given the octal values 2731.56. You need to convert it into binary. So what you can do, write the equivalent binary number. Okay, but you need to write it making pair of 3 bit. Like for 1 it is 001, not only 1. For 3 it is not 11, it is 011, 3 bit. In terms of 3 bit you need to write. So if you write equivalent binary with 3 bit, then you will get the equivalent binary for this octal values, right? So like similarly for 7 111, for 2 you can write 10 or 010, for 5 similarly 101, for 6 110, and for binary to octal into make a group of 3 bit, right? And done the reverse calculation what you have done here. For hexa to, for binary to hexa, so you have the binary values. For hexa you need 4 bits, so that's why take the 4 bit, this blue one, red one, then black one, this 3 bit, but in front you can consider 0 bit as well. Similarly this 4 and this 4. Write the equivalent hexa values, then you will get the binary equivalent hexa number, which is 5D9.B8. For hexa to binary, into the reverse calculation what you have done. So it's shown here as well for this example. Summary of conversion. When converting from binary or octal or hex to decimal, use the method of taking the weighted sum of each digit position. When converting from decimal to binary or octal or hex, use the method of repeatedly dividing by 2 or 8 or 16 and collecting reminders. When converting from binary to octal or hex, a group bits in each group of 3 or 4 and convert each group into the correct octal or hex digit. When converting from octal or hex to binary, convert each digit into 3-bit or 4-bit equivalent. When converting from octal to hex or vice versa, first convert to the binary, then convert the binary into desired number system. Binary coded decimal. Digital systems all use some form of binary numbers for their internal operation, but external world is decimal in nature. This means the conversion between decimal and binary system are being performed often. We have seen the conversion between decimal and binary can become long and complicated for large numbers. For this reason, a means of encoding decimal numbers that combines some feature of both the decimal and the binary system is used in certain situations. If little calculation is involved, we can use some coding sequence for decimal numbers. One such scheme is BCD, known as 8-foot-1 code. We represent each decimal bit as 4-bit binary. The main advantage of BCD code is that the ease of conversion to and from decimal, because in a digital system it is the logic circuit that performs the conversion to and from decimal. Binary coded decimal, which is known as BCD. If each digit 0 to 9 of a decimal number is represented by its binary equivalent, the result is a code called binary coded decimal or BCD. Since a decimal digit can be as large as 9, 4 bits are required to code each digit. The binary code for 9 is 1001. The BCD code represents each digit of a decimal number by a 4-bit binary number. You have given an example here, 874. This is the decimal. So for 4 equivalent, BCD is 0100, 4 bit. 7 is not 111, 4 bit is 0111. 8 is 1000. Similarly for 9, 1001 for 4, 0100 for 3, 0011. BCD to decimal. Convert this BCD to decimal equivalent to do so. Divide the BCD number into 4-bit group and convert it to decimal. So take this 4-bit and next 4-bit. So next 4-bit, next 4-bit. Write the equivalent decimal number. So this is 9386. So this is this BCD equivalent binary number. Again, you have given this number. Take 4-bit, write the equivalent binary number. So this equivalent binary number is not valid in BCD. So that's why it is called forbidden code group. So in BCD actually it is equivalent to 0 to 9, same as the decimal, but after 9 this is called forbidden group, like 10 to 15. Just look at here. So you can represent 0 to 9. This is 0 to 9 decimal and the red color is equivalent BCD, right? But 10 to 15, 10 means 1010, 15 means 1111. So this 6 bit is actually 6 number is unused in BCD. These code are considered as error. The advantage is it is easy to convert, but arithmetic operations are more complicated, suitable for interface such as keypad inputs and digital readouts. Comparison of BCD and binary. BCD is not another number system like binary, decimal, and hexadecimal. It is a decimal system with each digit encoded into binary equivalent. BCD is not same as straight binary number. A straight binary number makes the complete decimal number and represented in binary. The BCD code converts each decimal digit to binary individually. The BCD requires 12 bit while the straight binary code requires only 8 bit to represent 137. So if you look at 137, so binary you need 8 bit, and for BCD you need 12 bit, because for each bit you need 4 BCD bit. This is the chart where you can see decimal, binary, octal, hexadecimal, and BCD number. So 0 to 15, this decimal you already know. For binary you need to know 0 to 15, like 15 is 1111, like 10 is 1010. You need to know all of this. For octal, 0 to 17 it becomes for 0 to 15 decimal. So 0 to 7, for 8 is 10, 9 is 11, 10 is 12, up to 17. For hexadecimal, 0 to 9, hexa and you can say decimal is same, but for 10 decimal hexa becomes A, for 11 decimal hexa becomes B, and for 12 C, 13 D, 14 E, 15 F. For BCD, this is similar to your binary from 0 to 9. Just the difference is it is 4 bit, but for 10, so it becomes 448 bit. Like for 1 it becomes 0001 4 bit, for 0 it becomes 40. For 11 it becomes 0001 and another one 0001. So it goes after 15. For 15 it becomes, for 1 it becomes 0001. For 5 it becomes 0101.